Okay, hello everyone. I'm very excited to welcome all of you to the first ISyE seminar of this academic year. So our schedule this semester includes an outstanding list of speakers, and as a sign of slowly returning back to normalcy, we will have a mixture of in-person and virtual seminars throughout the semester. So today we have a virtual seminar as you all know, but next week we will have an in-person seminar. So I look forward to meeting everyone in person. So our speaker today joins us all the way from Paris. But before I introduce, let me briefly request that if you are comfortable, please keep your videos on and but keep yourself muted so that we don't hear any crosstalk. Feel free to unmute yourself to ask questions during the seminar. You can also post it on chat and I can ask the question on your behalf during the seminar. So with that, let me introduce Professor Florin Ciocan. He's an assistant professor of technology and operations at INSEAD, Paris. He holds a bachelor's degree in applied mathematics from Harvard and a PhD in operations management from MIT Sloan. His research interests are in the applications of revenue management to non-traditional domains such as online advertising, internet facilitated marketplaces. I have the honor of being his co-author on a paper, so that's another thing. So he is interested in cloud-based optimization methods for massively sized data sets. And today he's going to present his research on price delegation with learning agents. So with that, Florin, thanks for accepting our invitation, and the floor is yours.
Thanks, Chris. So hi, everyone. It's a pleasure to be giving this talk, and really nice to get to meet all of you. Looking forward to the discussion that we'll have during the talk and after it as well. Like Chris said, my name is Florin, and I'm a professor at INSEAD in France. So I'll be talking about some work that I've been doing with colleagues of mine at INSEAD, Atalaya Tasu and Antoine Desir. And this is actually a paper, so price delegation of learning agents. And this is a paper that we've just finished. I mean, we've kind of been saying we've just finished it for the last couple of months, but I think now we've actually properly just finished it. So hopefully we'll be submitting it in the next couple of weeks, and thus this talk is very timely for us. So any comments, questions, feedback that you have on it will be very, very useful for us. And I think I don't have too many slides, so I don't think that time should be an issue. So if you need to interrupt me with any kind of comments in the middle, please feel free to just go ahead and do it. Yeah, so maybe I'll get started. And I hope I apologize. I'm trying to prove to myself that I'm still young enough that I can be sort of coherent and interesting beyond 10 p.m. So hopefully I'll be able to do it. Don't tell me at the end whether I've done it or not, because maybe I don't want to know, but hopefully it will work. So at a high level, what is this paper about? Well, our starting point is actually a very classical type of question from revenue management and from pricing. So here's this classical question. You're a firm and you have K units of inventory of a particular type of good. Your customers, let's say there's N of them, each one of them has a valuation drawn from some common distribution. They arrive sequentially. And what you want to do is you want to think about how to set prices to show to these customers so that, broadly speaking, well, you maximize your own revenues, your own payoff as a firm. And like I said, I mean, this is a very classical problem, and it's a problem on which lots and lots of papers have been written, and a number of you in the audience have written papers on this. And maybe the seminal result in the stream of literature is the paper of Gallego and Van Rysel. And what it says is that for such a model, what you want to do is you can just show a fixed price to all the customers. There's a relatively simple optimization problem that tells you what fixed price you wanna show, and this is in an appropriate sense good enough. So this is the starting point. And maybe the question being that this is such a prototypical problem, well, what is there new, or what is there missing from this model that we can tackle in a research problem? So I hope that by the end of the talk, I'll be able to show you that there is something that's important that's missing from this picture that I'm showing you here. And it's important practically, and it's also an interesting research question. So what is this? Well, if you look at a lot of commerce, and kind of the typical feature in the commerce that I'm focusing on here is sort of very big ticket items that get bought and sold, traded, etc. Well, in a lot of this commerce, actually the firm doesn't get to interact with the customer directly. And also by implication doesn't actually get to set the prices directly to the customer. In fact, in a lot of commerce, what happens is that there's an intermediary in the middle, so a salesperson, and it's actually the salesperson that manages the sales process of the customer. The salesperson has a lot of delegation on how to interact with this customer, and they're the ones that actually represent the firm. So the firm doesn't actually directly make decisions, doesn't actually have a direct interaction with the customer. So what's an example? What are examples of these types of applications? Well, the one that we started out with, so my colleague Atalay, and he suggested this problem initially. He was talking to a pricing analytics company, and one of their customers was a real estate rentals customer, and their salespeople were trying to figure out, or rather, they were the ones who were kind of interacting with the customers, and they were trying to figure out, well, what kind of prices and what kind of ways to incentivize the sales force should we use to get the best revenues, to extract the best revenues. And I should also say that in this kind of situation, actually, before even getting into specific applications, the sales force is given quite a lot of power by the firm. In particular, the salespeople might be given price delegation. So what does price delegation mean? This means that actually the salesperson has the liberty to decide the price that it's going to show to any particular customer, rather than the firm enforcing a price on the salesperson. Okay, so like rental, the previous example that I gave you, real estate rentals, that's an example of that. Like salespeople there can tailor the prices to the actual customers they're talking to. If you've been in a car dealership, you've probably been subjected to that as well. And financial asset transactions, for instance, if you're talking about assets that are not super liquid, so that there's sort of an exchange where the price is very clear. If it's an illiquid financial asset, it's actually a little bit unclear what the right price is. So if you're trading, if you're a broker dealer and you're trading with a customer, you actually have you have quite a bit of price freedom in terms of what price you're actually going to show to that customer for buying and selling securities. So just generally, this kind of phenomenon of price delegation is actually something that happens in a lot of commerce. And I think nowadays we think a lot about e-commerce and sort of fully automated customer interactions. Like you just go and you check something out from a cart. But actually, there's a lot of commerce that still looks like this, and arguably will always look like this. Like there's a sales force in the middle, and the sales force actually gets to call a lot of the shots. So basically, the phenomenon that we're going to focus on in this paper is this phenomenon of price delegation. And I don't want to claim that this is the only reason why price delegation might happen in practice, but I think this is certainly one of the important reasons why price delegation happens. So why do firms actually give salespeople the power to set these prices, freedom to set prices? Well, basically, I think it comes down to a very simple principle, which is that it pays to know the customer. So because it's the salespeople who actually get to talk to these customers and interact with them, well, it stands to reason that these salespeople, they can actually collect lots and lots of information about the customer's features, and effectively collect a signal about the customer's true valuation. And if they actually get good signals, if they actually get high quality information about the customer's valuation, well, then it stands to reason that you might want to actually give them the freedom to do the pricing decision as well, because they'll be doing pricing, they'll be computing prices with just fundamentally better information than the firm itself. Okay, so basically, in a nutshell, salespeople can actually learn the customer evaluations much better than the firm itself. And they can use this information to price better than the firm. So hopefully now we're kind of converging towards a problem that's different from the classical problem that I started out with, and that hopefully you'll find interesting. So the problem is essentially, if you have a system like this where there's a sales force in the middle, the sales force actually gets to set the prices. The firm can no longer set prices, but it can, as a control, if you want to think about it that way, as a control, they can figure out a compensation mechanism for the sales force. Well, then how should the firm actually set this compensation mechanism to actually induce the optimal agent learning and pricing behavior? Okay, so prices, it's still a pricing problem in my mind, but the firm, the decision maker, no longer has direct control of the prices. They have the direct control on a compensation mechanism to the sales force. Okay. Can I pause here for a second, just in case there's any questions about this kind of high level model?
So can I ask a question?
Sure.
Just in terms of like trying to understand. So even in like these platform settings, I mean, you can think, I mean, there are many platforms where the platform either sets the price or at least suggests some price to the individual sellers or something, right? Like, for example, Airbnb, like there are these price recommendations that are given.
Yeah.
So that is, that would not fall in the setting like this, because here you're assuming that the firm is the one who's designing the compensation mechanism, and not the sales force, or is that something?
Well, so the firm is the firm is the one that's designing the compensation mechanism. So the firm, I think if you want to think about it from a control perspective, the control of the firm is the compensation mechanism itself. And then given a compensation mechanism, prices are the control of the sales force. I think the setting that you're talking about, I mean, I think it's a very, very interesting setting, because you can think about, so I think what that would mean in this model, it would mean that salespeople set the prices themselves, they do the learning themselves, but maybe they can get some side advice, or they get some price recommendations or whatever from the firm itself. And I think that would be a very, very interesting research question, but it's sort of on top of what we're actually doing here. And I don't want to claim that we can actually tackle that that kind of situation in what we've done here, but I think it would be a very, very interesting question. Like, in some sense, what we're trying to say here is that, you know, there's settings where the salespeople can collect a lot of idiosyncratic information that the firm cannot collect itself. And then you give them a decision to make that uses that idiosyncratic information. In reality, probably the firm also has some information on it by itself that the salespeople don't have. And they could, and you know, there's a question of how you combine these things, but it's kind of beyond what we're doing here.
Okay, thank you.
Yeah.
Could I ask if you could translate the following problem into your case, where there is a list price and the salesperson is delegated to be able to come up with a discount that is specific to the customer?
Yeah, so it translates. It doesn't translate perfectly, but it does. So I mean, what we're saying here in our model, the salesperson can set a price P. You will see that in our model, it has absolute freedom in terms of what price P to set. But the sort of situation that you're describing is one where the sales force still sets the price, but it sets the price by actually choosing a level of discount. So, you know, sort of the starting price, the maximum price it's another piece of information that the firm sends to the sales force, but then the sales force has discretion of, you know, do I do 100% of that price, 90% of that price, 0% of that price. So it would fit perfectly into the model here if we, in addition, we added some kind of bounds on the prices that the sales force can offer. Okay. And I think practically that's how a lot of these things are implemented, because I mean, it's a lot easier to actually do discounting operationally and also from a regulatory perspective than to, you know, sort of say that you're doing targeted pricing. So I think in practice, the way that this would show up as is some kind of form of discount that the salesperson is doing.
Thanks.
So, okay, at a broad level, that's what we're trying to do. So if you have salespeople who learn, they have price delegation, how do we express that as a revenue management pricing problem, and what can we say about it? So having said this, maybe let me start building up our model for this. So in our model, we're going to have capital N customers. And let's say that each one of these customers show up in a time period. So basically each time period is equal to a customer arrival. So there's N customers. The firm and the agent has K units of inventory of a good to sell over the entire timeline of these customers arriving. And thus in each period I, there's a customer arrival, and the agent, the salesperson, actually interacts with this customer I. This happens over all of the stream of customers. And then at the end of the day, the agent receives a reward T, and the reward T depends on what's actually happened in terms of the sales to all of these customers. Okay, so it stands to reason kind of what's interesting in our model is what will actually happen inside one of these customer interactions inside one of these time periods I. So let me sort of zoom in into this picture, show you what happens inside one of these time periods. So what's going to happen in our model? So in time period I, customer I will arrive. They get a valuation that's drawn from some common distribution with density capital F. And then there's actually two decisions that the agent is making. So the first decision is a learning effort decision. And this is a binary decision that's E index I. So what does this mean exactly? Well, this effort, it's something that's unobservable to the firm. So the firm can't really tell directly whether the agent put in effort or did not put in effort. But what happens is once the agent actually makes this effort decision, if the decision was, let me actually set EI to 1, then there's full learning that happens. So what does this mean? If the agent puts in a full learning effort, then they learn the true customer valuation VI. They learn the realization of the customer's valuation, which obviously is good, but there's a trade-off in that this kind of effort actually has a cost. So it costs them this value psi for them to actually learn the customer valuation. On the other hand, the agent can choose to not put in this learning effort. They set EI equal to 0. This is costless, but then they learn nothing more beyond the common distribution of the valuation that was known prior to this effort decision. Okay, so this is basically a decision that just says, do I try to learn the customer's valuation or do I not try to learn? Do I talk on the phone with the customer for a long time and ask them lots of questions, or do I just not do that? So, okay, that's the first decision. Now the second decision, after this learning has happened or not happened, the agent actually makes a pricing decision. So they pick a price PI, and this price PI that they pick is something that will depend on whether there was learning or not. In the sense that if EI was equal to 1, then the agent will use a so-called informed price. So what the informed price means is that the agent actually now has access to the true VI. So they're going to tailor the price that they show to the customer to this information they have to the customer's true valuation. Okay. And on the other hand, if the agent has not learned, then they'll use a so-called uninformed price. So they don't know the true valuation. Basically, what they can do, the best that they can do, is use the optimal fixed price of Gallego and Van Rysen affected. Okay, so basically, if there's learning, you tailor the price based on the customer's valuation. If there's no learning, you just use a fixed price a la Gallego and Van Rysen. Okay, any questions about this? So, by the way, I could ask you in this informed price case. So I said there's going to be, you're going to use a price that's this theta VI. Okay, you can imagine that theta of VI will probably be equal to VI. Okay, so I learned the customer's true valuation, and I just price exactly at that valuation. Okay. I've written it in a slightly more complicated way here as a general function of the true valuation, because we'll see that you may not always want to use exactly VI. Okay, but for now you can imagine that probably what you want to do is use theta VI equal to VI. Okay? And then a policy will just be a sequence of these learning efforts, so the EIs, and then the informed and uninformed prices that you'd want to use. All right. So now, at a still at a slightly high level, what is the contract design problem that we're tackling here? Well, at one level, you can think about the agent's best response optimization problem. Okay. So what does this say? If the firm offers the agent a contract, a reward function, little t, what the agent will do is it will pick a learning and pricing policy, pi t, that maximizes its own profits subject to the sales of that particular policy being less than or equal to k. So subject to an inventory constraint. Okay, so I get a contract t from the firm, and then I calculate a policy that's a best response with respect to that contract. Okay, so that's the agent's best response optimization problem. But then on top of this, there is the principal's optimization problem, okay, which is an optimization problem over all contracts. Okay, so let me search over all contracts and try to maximize the expected revenues from the policy that would be induced by a contract T minus the payment of that contract T, but then subject to the constraint that this policy better truly be induced by the contract T. So in other words, it better be a solution to the agent's best response problem, okay, which is an incentive compatibility constraint, if you want to think about it that way. Okay, so there's sort of these nested problems. The principal's optimization problem is a search over contracts, but inside there's a constraint, there's an incentive compatibility constraint inside that problem that basically makes sure that the policy is actually consistent with the agent's best response. Okay. So what do we know about this type of problem? And also, maybe what makes this type of problem hard? Okay. Well, maybe let me give you a sort of brief literature review. So what are the kind of relevant research streams to this type of problem? Well, you can probably already see that this is a principal agent type of problem. So these kinds of problems where you have an agent that represents the principal, the agent can put in some kind of effort that's unobservable to the principal. These are so-called principal agent moral hazard problems. And they're something that have been studied in economics for a really, really long time. What I have here is just a list of, sort of very representative papers in that economics literature. There is a typo here. The last paper is not Carol Merle's. I don't think that they've actually written a paper together. Merle's has his own paper from 1999, the first one in the list. But there's a very established stream of principal agent problems in economics that have actually also made their way into the marketing OM interface. So there's a stream of papers there that have looked at Salesforce compensation when the Salesforce can put in some kind of unobservable sales effort. So that's Diane Giraffe. There's a sequence of papers there, Oyer, Chun Lai, Xiao, and Xiao. Another stream on sales effort combined with discretionary pricing. So discretionary pricing is what I'm talking about here. The agents can pick the prices themselves. And then one last paper that I think is the one that's most closely related to ours, which is directly looking at price delegation and learning. And that's Phillips and al. 2015. Okay, so I'm saying that that's the paper that's closest to ours because in that paper, they do look, I think in the context of car sales, at salespeople who can learn and then price. The difference between our paper and that is that is an empirical paper where they look at this phenomenon empirically. Basically, what we're doing is we're sort of doing the optimization side of things. We're asking, well, what is the optimal contract that you can offer in this kind of situation? There's one very, very important distinction between what we do and what this literature does, at least all the papers except the Phillips and all. In all of these principal agent moral hazard problems, you look at so-called demand shifting effort or sales effort. And what that means is that the agent, through their effort decision, can change the demand curve. So they sell a little bit better and they increase the demand for the product. In our language here is maybe the salesperson, they put in effort and they increase the valuation of the customer by a little delta. So that's actually quite different from the learning effort that we're talking about here. So in our paper, effort does not change in any way the demand or the valuation of the customer. It simply gives you information about that valuation of the customer. Okay. And then after this, obviously there's a very large body of work in revenue management on this. There's work on pricing with inventory, starting, like I said, with Gallego and Van Ryzen, but really very, very rich literature there. I think Bill has written a number of papers on this, just lots of work there. Maybe also another relevant paper to us, there's a paper on price bargaining, where a salesperson can actually learn about their sort of opportunity cost through through interactions with multiple buyers, but there's no concept of an agent. There's no principal agent concept in that paper. Okay. But now, with respect to that literature, what's new in this optimization problem that I was showing you? There's two very big differences, I would say. So first of all, when we compare to principal agent with demand shifting or sales effort, like I said, our learning effort is actually quite different. And it's quite different because in our model, there's sort of a 2D nature of agents' actions. So there's an effort action, and then there's a price action. Okay. And the other thing that's tricky is that the price action actually depends on the effort action, and it depends on the contract itself. Because you can imagine that the price that the agent will select will depend on, the shape of the reward function that they get for selling at that price. Okay. So what does this actually mean? If you think about typical principal agent sales effort problems, the typical way that you get some kind of result there is you generally have, so you can imagine if you look at the firm's profit as a function of effort, basically you make some kind of statistical assumption on the distribution of profit as a function of effort. That statistical assumption, the most common one, is something called the monotone likelihood ratio property, MLRP property. And that allows you to get some headway on how to solve the problem. What is different with learning effort is that, at least as far as we can tell, this MLRP property doesn't really work. There's no way to extend that property to our learning effort case. And that really kind of comes from this effort plus pricing nature of the problem. Because in our problem, if you look at the distribution of firm profits, it's actually something that will depend not only on effort, but on price, and price will actually depend on the contract. So there's an additional kind of degree of freedom of endogeneity in the problem that kind of makes this MLRP type condition not particularly useful for us. And then the other issue that we have is that we have inventory. So we have multiple goods, and in the presence of multiple goods, you'll have essentially a dynamic mechanism design problem, because now what the agent does for one customer is linked with what they'll do for the future customers. And these kinds of dynamic mechanism design problems are just generally very, very difficult to deal with. So that's kind of a picture, the two main ingredients in this work that I think make it sort of technically challenging. So having said this,
can I ask a question?
Yeah, go ahead.
So the policy, so the agent's decision is independent of the history, right? In your model?
So yes. So the way that I wrote it is it's independent of history.
Okay.
Yeah. But it's enough. So basically there wouldn't be a loss from just making it independent of history.
Okay.
So I think this will become clear when I get into the results. There's going to be a fluid model in there that will guarantee that happens.
So the agent doesn't care how much inventory is left?
Yes, because if the agent actually looked on a path basis how much inventory is left at a particular interaction with the customer, a particular time step, you would have a nightmare of a mechanism design problem. I mean, you can imagine that even writing down an incentive constraint would be very, very difficult to write down. So that's why, to get rid of this, what we'll do is we're going to look at a model that's a fluid model, where basically the agent just thinks about the initial inventory, but then doesn't worry about anything bad that could happen kind of in the interim, in the state evolution, in the trajectory of the system. So I think this will become very clear when I get into this. Because what I'll do is I'll show you results for two different models. So we're actually going to start with, in some sense, a warm-up. So I'm not going to even get into the sort of complicated questions that you guys asked. I'm going to study a simple model with a single customer, single inventory, single unit of inventory, so no history to worry about. I'm going to show you a contract that works there. And then we're going to move to a general model with multiple customers, multiple units of inventory where these might be issues. And I'll show you some results there, but again, under a fluid assumption. And that's basically the rest of the talk. So let me get into this. So the single period model first. In the single period model, like I said, k equal 1, n equals 1. And let's just make some preliminary assumptions in this kind of model. So let's assume that the principal wants to induce full learning. So we're in a case where the problem is such, the problem instance is such that the optimal learning from the firm's perspective is equals 1. Okay, and this is the interesting case to worry about. If they don't want to induce learning, then they just don't pay the agent anything, and that will do the job. So you're looking at the equals 1 case. We're gonna optimize over the space of non-decreasing contracts T of V. So basically the higher sale price the agent receives, the higher their payment. And the consequence of this is that in that case, if you learn the customer's valuation, you want to price exactly at that valuation. So the informed price theta of V will be exactly equal to V. And then we're also going to assume that the valuation distribution capital F is continuous and it has increasing hazard rate. Okay, so some hopefully reasonable assumptions that we're making. So if we do this, well, maybe the first question is, how do we even know that we've gotten our hands on a contract that's good? So in this kind of principal agent problem, how do we think about contract optimality? Well, the way that this is usually done in economics, and I think Chris already used the term first best at the start of the talk, we look at something called the first best benchmark. So what does this first best benchmark say? Well, first best is sort of a thought experiment where you say, look, a lot of the contracting problem is the fact that the firm cannot directly observe effort. So the effort is so-called unobservable. But what would happen if effort was actually observable? Well, then if you observe effort, you could directly contract on whether the agent has put in effort equal to 1. In which case there would be no moral hazard. And there would be no incentives to worry about. So the so-called first best problem would simply be, well, you want to maximize the expected value, that's the difference between how much you make in firm revenue. So remember that now theta V is equal to V. So the agent learns. They were priced exactly at V, and that's how much the firm makes in revenue, minus the payment that the firm has to give the agent, okay, and just subject to a participation constraint that says that the reward of the agent has to be at least their cost of learning psi. Okay, so this is a very, very simple first best problem in this single customer, single unit case. It provides an upper bound on how much any kind of contract in the unobservable case could actually make the firm. So this is an upper bound effectively. And it's a simple problem to solve. So you can probably see that the solution to this problem is any contract where the participation constraint is binding. So basically any contract where the expected value of T of V is equal to psi, this will be a first best optimal contract. Okay. Now the question, and this is the typical question that economists ask, is, well, can I actually implement this first best benchmark? So in other words, can I make as much money as the firm would make in this first best benchmark in the real case when effort is unobservable? Okay, so for the rest of the talk, that will be the central question, both for the single customer case and the multiple customer case. We'll write down this first best benchmark, and then we're going to have to think about, when effort is unobservable, can we actually write a contract? Can we find a contract that achieves this first best benchmark? Okay, and quick peek into what we're doing next. It actually turns out that you can achieve this first best benchmark. So there is a contract that will give you J first best, but there's a big catch to this. And the big catch is that in this contract, it could be that the firm actually penalizes the agent for no sale. So what does this mean? Well, when we get paid from our respective schools, we always get paid. There's no state of the world where we actually have a salary that's negative where we have to pay the school. Effectively, I mean, hopefully, what happens in this contract is that in this contract, there will actually be negative payments. So there will be some states of the world where the agent would actually have to pay the firm. And it turns out that to achieve first best, there's no way to do it except by having these kinds of contracts with penalties. Okay. Now, obviously, that's not very practical and not super interesting. And that's why what we actually focus on is contracts that are so-called limited liability contracts. Okay. And what limited liability says is that simply, well, the firm always has to pay the agent something. Okay. So there's no state of the world in which T of V is actually negative. T of V is always non-negative. Okay. And at this stage, this is not particularly surprising. Like if you talk to an economist who's a principal agent person, they'll say, well, I generally know that if I don't have limited liability, I'll be able to find a contract that implements first best. But it's usually when you impose this limited liability constraint that things get a little bit dicey. And for many problems, you actually cannot implement first best. So actually now what we're going to talk about, and this is kind of the meat and potatoes of the results, is what can you do if you want the contracts to be limited liability? So with limited liability and with unobservable efforts, well, we need to worry about incentives. So let's write down an ISyE constraint for the agent. And the ISyE constraint looks like the equation at the top of the slide here. So on the left-hand side, what we have is the payoff of the agent in the case that they actually put in learning effort. So if E equals 1, then they will get a payoff that's equal to E of TV, but they'll pay a cost psi. Okay. On the right-hand side is how much money they could make if they didn't put in learning effort, and they simply used an uninformed price. So they effectively did fixed pricing. Okay. And what this says is it's the max over all possible prices of the expected revenue that I'll make from setting that price. So that's T of phi, F bar of phi. Okay. And then the problem, the firm's problem becomes you want to maximize over contracts. The payoff of the firm, which is still V minus T of V, but then subject to the old participation constraint, plus this new ISyE constraint, plus a limited liability constraint. Okay, so we need to solve that problem now. Here's some intuition on a contract that should solve this problem. So what I'm doing here is I'm rewriting the incentive compatibility constraint. It's the same thing as from the previous slide. And what I want to argue is that on an optimal contract for this problem, I should actually see T of psi times F bar of psi equal to a constant. So if you look at what's inside the max on the right-hand side, okay, basically the firm should be indifferent to any price. Sorry, the agent should be indifferent to any price in terms of this expected revenue from that price. And why is that? Well, if you think about plotting, so on the x-axis, you plot the fixed price that the agent uses. On the y-axis, you have the expected revenues of the agent. Okay, you can think about if this was not constant, it was some like curvy line like this. Well, basically, you'd have to go and look at the maximum on that line. Okay, and because of the ISyE constraint, the actual expected payment of the agent, which is E of T of V minus psi, would have to be exactly at the max of that curvy line. Okay, and now if there is a unique max, if there's actually like a top to this, well, what you could do is you could simply lower the price there. Okay, now this entire right-hand side, like max of T of phi, F bar of phi, goes down. Okay, so you've created a little bit of slack in the ISyE constraint. So you can actually lower the expected payment of the contract a little bit, and you'll end up with a better contract for the firm. Okay, so the place where you'd end up is the one where actually all of this T of phi times F bar phi is constant, where you can't make this change anymore. Okay, so what's a consequence of this? Well, intuitively, at an optimal contract should be proportional to this 1 over F bar of phi. Okay, and what we'll show is that that is the optimal contract, but subject to one technical caveat. So what's the technical caveat? Well, if this was really the contract, then the expected payment would be E of 1 over F bar of E. And you can actually check that, for most distributions, that would be infinite. So if the contract is exactly like this, it sort of wouldn't be well defined. So what we need to do is we just need to tweak this contract a little bit to get our result. But effectively, this is the optimal contract. So how do we tweak this contract? Well, we define a sequence of m-bounded problems that are the same problem as the one that I was showing you before, the same agency problem, but one where we add an additional so-called m-bounded constraint, where we impose the constraint that T of V is less than or equal to M. Okay, so we impose an upper bound on the maximum payment that the contract can pay. Okay, and now what I'm going to show you is there's a contract family. Okay, and what the contract family is exactly what I'm showing you in the graph here. Okay, so it's something that's proportional to 1 over F bar of V, like in the previous intuition. But then it's actually something that's capped after a certain part at this capital M. Okay. So effectively, what I've done is I've taken the contract from the intuition, but I've just capped it. On the right tail, I've just capped it at a capital M after a certain point. Okay. So what I'm actually going to show first is that a contract in this family is optimal for the m-bounded problem. Okay. So as long as I tweak the real problem by just adding this additional m-bounded constraint, I can solve it and I can find the optimal contract for it. And this is the proposition that does it. So basically the statement is that basically for every m, for every such bound, I can find a point where I impose this bound in the contract, and thus I can find a contract that will actually solve the m-bounded problem. And moreover, this is a key thing in the statement, is that if I look at the rent extracted by the agent, okay, and what I mean by rent is just the difference between the first best firm payoff and the payoff that you get in this unobservable effort case, well, that rent will actually go to 0 as this capital M goes to infinity. Okay, so in some sense, as M goes to infinity, as I pick larger and larger caps on the payment, as M goes to infinity, the effect of first best, the effect of unobservability, the loss from first best from unobservability will actually go to 0. Okay, the proof of this is via a primal dual argument that actually shows the optimality of the contract in the m-bounded problem. And this is an optimal result from the m-bounded problem. Now, to actually go to the real problem, there's actually a fairly simple bridge to go to the real problem. And for that real problem, this is effectively the result. That is just a corollary. So the result is that for every epsilon, okay, and epsilon is simply an error term, an additive error term, I can actually find a contract by choosing an appropriate capital M that is epsilon optimal. Okay. So the firm payoff from using this contract is at least J first best minus epsilon. And furthermore, this contract is actually the right contract in the sense that it satisfies participation, it's incentive compatible, and it's limited liability. Okay. So what's nice about this? Well, in English, what this says is that even in the presence of limited liability, the firm can actually approximate first best to arbitrary precision. Like I said, this is actually a result that doesn't hold everywhere in the principal agent literature. So if you look generically at principal agent problems, it's actually quite unique and it's quite non-trivial that first best can actually be approximated to any arbitrary precision. In general, there's a rent to be extracted versus first best. Okay. Now, a discussion about this that I think is interesting to think about is that, remember, I actually started this talk and I started this baseline model by saying that because we're doing both learning and pricing, you have this 2D action space for the agent that actually makes the problem much more complicated. In particular, it removes this MLRP property that's been used in the literature before. But I think what is to be seen from this contract is that the firms, the flexibility of the agent to actually price, okay, to have complete price delegation, is actually something that the firm is using. So why is the firm using this? Well, remember that the price, the contract is essentially 1 over F bar of P. Okay, so let's think about what the contract is actually doing. Well, you can think about the sale price that the agent achieves. Okay, and you can only sell at price P if the customer's valuation is greater or equal to P. Okay, so let's think about actually the distribution of customer valuations. Okay, and let's think about the tail of that distribution. Okay, so if you sell at P, then the valuation must be on the tail, the right tail at that P. Okay, so now if you think about what the contract is doing, so on the y-axis we have the payment of the contract. What the payment is really doing is it's actually paying the agent very little for sort of typical customer valuations. Okay, but it's paying the agent a lot of money for sort of very atypical, very high customer valuations. So really what you're doing is you're kind of balancing things. The agent gets very little for the sort of typical sales that they can achieve, but they're promised extremely large payments if it happens that the customer has very high valuations, and in that case, they're paid like just a gigantic amount of money. So basically, the ability of the agent to price is used by the firm because the firm is effectively offering the agent a lot. And it's basically this lottery itself that kind of achieves that kind of allows this first best approximability result. Okay, so that's just kind of a discussion to keep in mind about the shape of this contract that I'm showing you here. Okay. Here I have just one slide where I'm showing you some numerical examples of how quickly the contract, as n goes to infinity, approaches the first best. Don't have a lot to say here. I mean, that's just the convergence that can be seen numerically. Okay, so maybe now I want to also say a little bit about the multiple customer model. But maybe before I say that, let me just pause for a sec in case there's any questions.
So Florin, we have about like 6 minutes, so maybe we can hold the questions after the
Sure.
talk. Yeah.
Sure, and I think I can probably finish in like 5 minutes or so. So hopefully we'll still be on time. So that was the result for the baseline model. Now, what can we say about the general case where there's multiple customers and there's actually inventory? Well, there's one big simplification that we'll be making, which is that we'll be giving an answer to this problem, but in a fluid regime, where basically everything, all the relevant quantities are actually replaced by their rates or their expectations. What does this mean in a nutshell? What I think in a nutshell, all that it means is that, or really the key simplification that we're making is that the agent needs to make decisions respecting an inventory constraint. So what we're going to be doing is, instead of actually enforcing this inventory constraint almost surely, we'll just be making sure that on average, the number of sales that the customer, that the agent will achieve is something that is less than or equal to K. So basically the inventory constraint will be enforced in expectation. Now, how do we say something about this model? Well, effectively, what we'll be doing is, again, we'll be starting with the first best benchmark, but now we'll be formulating the first best for this large generalized problem. And effectively, what we'll be doing is the first best benchmark will be an upper bound on the firm's optimal payoff J star. And effectively, the proof strategy will be to actually solve the first best and find the optimal policy, the optimal learning and pricing policy that the firm would want to use if it was actually in this first best scenario. Okay, so we'll get a first best policy pi FB. Okay, and what we're going to do then is we're going to actually find a contract, okay, that is consistent with pi FB. Okay, that is pi FB will be incentive compatible and inventory feasible with respect to this contract. Okay, so that means that if the firm actually offers T, it will induce a policy pi FB on behalf of the agent. And then what it will come down to is little t, the contract little t, will give the firm some payoff JT. And then the question will be, well, how close is JT to J of FB? And we'll have a result on that. Okay. Just to give you a bit of a sense of how the problem complicates. Well, JFB is actually a lot more complicated now. In particular, now the effort decision is, or rather the effort decision is randomized. So at every period, the agent basically generates a Bernoulli random variable of probability QI that decides whether they put in learning effort or not. Now, the first term in there is the revenue under full learning. The second term is the revenue under no learning and using the fixed price and informed price. And then the last term is the payment. We have an inventory constraint. This inventory constraint will have some Lagrangian penalty lambda. And the other thing is that now if you think about, if you learn the customer's true valuation, your optimal informed price may not always be equal to VI. Okay, and it might not be always equal to VI because what could happen is, now if you have multiple customers, you have multiple opportunities to sell the same unit of inventory. So you could actually learn the customer's valuation, learn that it's a pretty low valuation. And in that case, your best informed price might be essentially infinity, so that you don't sell to the customer and you wait till the next customer that will hopefully show up with a higher valuation. Okay. So the phi policy is, the theta policy is also a little bit more complicated. Now, it actually turns out that the optimal policy in this first best problem can be of three types. Okay, and what's interesting is that these three types basically depend on just a very simple measure of inventory scarcity, which is this rho, which is K over N. So how many units of inventory you have versus how many customers you have. And it turns out that there's three regimes. So there's a regime where you do no learning on any of the customers. So your optimal policy is this pi no learn. And this is in the case where you have very little inventory. And if you have very little inventory, you have many opportunities to just use a high fixed price, never pay the cost of effort, because there's enough customers that in the end you're going to find a customer who will actually buy at that high fixed price. At the other end, you have it could be that pi learn is that full learning is optimal. That's in the case where you have lots of inventory. So in some sense, every customer is very valuable. So it's valuable to actually learn on every customer. So use learning on all of them. But you also have this regime in the middle that's actually a pain to analyze technically, which is this partial learning regime. Neither is particularly scarce, and what you do here is you wanna use some kind of partial learning policy where you learn on some of the customers, but you don't learn on some other customers. Okay, so I'll just to try to conclude. Basically, now what we want to do is we want to start with this first best policy pi FB, okay, and like I said, I want us to guess a contract T that can actually implement this pi FB. Okay? And the trickiness is that implementing is actually complicated. Like you need to have incentive compatibility, you need to satisfy this inventory constraint. What's actually nice is that you can do this with a pretty restrictive contract family. So now if you have multiple customers, it could be that the contract could be very, very complicated. Like it could depend on the sale price on each customer in like a super nonlinear way, you know, whatever could happen. It actually turns out that a contract that's separable in the payment of each customer is good enough. So we're going to focus on contracts where the total payment of the contract is just the sum of our customers of sort of a single customer contract, TI. The single customer contract will be static. In some sense, this is a consequence of the fluid model. And it will be limited liability, non-decreasing, and it will turn out that this is sufficient. So what contract does the job? Well, remember the contract that we were using for the single customer baseline case from like 10 minutes ago. Okay. Here's a small tweak of that single customer contract. So what's the small tweak? It's still something that's proportional to 1 over F bar P. It's still capped at a big M somewhere. The only change is that now, below a certain threshold of the sale price, I'm actually paying the agent 0. So what's the interpretation? Well, you can think about this as a contract with a reservation value. So this price P that the agent can produce, it competes with the reservation value. If it's below this reservation value lambda, then you just don't actually sell. Okay. And the main idea for the result is we're going to show that this contract is enough. And we're actually going to do this by just setting this threshold, this lambda here, to exactly the Lagrangian dual from the first best problem. So we're going to look at the first best problem firm's sort of cost of inventory. We're going to use that as a reservation. Now, the trick is that that's the optimal Lagrange multiplier in the firm's first best problem. It's not clear at all that that should be the optimal Lagrange multiplier. It should do anything good for the inventory constraint that the agent in the agent's problem. And basically, that's the proof that actually works. But it's not a priori clear that that's true. So now I'm getting near the end. What this corollary says is, you know, and just very, very quickly, basically what this corollary says is that now with this contract, in the multiple customer inventory case, the same thing happens. So this contract that I'm showing you will be epsilon optimal. So it will be epsilon away, at most epsilon away from J first best. And it will be a valid contract in the sense that it will satisfy participation, ISyE, and the inventory constraints. Okay, and again, kind of the key idea is to inject this kind of reservation value into the single customer contract. Okay, so I did finish a little bit later than I thought I did. To be honest, I thought I was going to finish like 20 minutes ago when I wrote these slides, but okay, no. But hopefully, you know, I've shown you a new angle on what, you know, to start is a classical pricing problem. And I think that, you know, it's actually really, really interesting and important to acknowledge that, you know, in a lot of commerce, you know, things look different. You have these agents, and the incentive problems with these agents are actually important. And I think there's very, very interesting kind of avenues for future work on this to think about. So that said, sorry for running a bit out of time, and you know, hopefully there's still a little bit for some questions. And thank you.
Yeah, thank you, Florin, for a great talk. Yeah, so we do have a reception following this. So anybody who wants, we can stay here and ask questions. But of course, we're looking at the time. If anybody wants to leave, they can leave also. Yeah, so the floor is out for questions.
So, Florin, I have one question, and for the multiple customers case, I'm thinking of what the optimal experimenting policy would be. Is it like there is some rate at which I'm experimenting and that rate changes with the approaching horizon?
So what do you mean by an experimentation rate?
So I have to make a decision about whether to learn or not, right? Put an effort or
Mhm.
not.
Yeah.
So effort. So now, because here again, you have the decisions are independent of the history, right?
Yeah.
So but you are still making decisions about how much effort to put. So
Yeah, so I think it would be this QI here, right? Is that what
Yeah.
you're thinking about?
Yeah.
Yeah. So I mean, I think, so you're thinking about what would happen in a, if I understand the question correctly, I think you're thinking about what would happen in sort of a full dynamic model. So what's different, or what's the key thing in the model that I'm showing you here, is that I'm enforcing because I'm enforcing this inventory constraint and expectation. Really what happens is, you can imagine that the agent solves a one-shot problem. So like there's a T-1, and you solve a one-shot problem there. You decide all these QIs. It actually turns out that all the QIs are static. So you basically just decide a single Q, and then you follow that. And the point in this fluid problem is that you follow this rule, and it could happen that you consume inventory a little bit slower or a little bit faster.
Yeah.
And that's something that you need to worry about in terms of how good the fluid approximation is. But in the fluid model itself, that becomes a non-issue.
Yeah. So you have a fixed experimentation rate, fixed learning rate. Yeah. Right. Okay.
Not only that, I mean, it's fixed, and it's not contingent on the states. Nothing changes in the interim of the timeline.
Yeah. Okay. But even in the fluid model, you may expect, but apparently your results say it's not. But I was wondering if it would be a dynamic, a time-dependent experimentation rate.
I mean,
even if it's history independent, but it could be time dependent, right?
Yeah. So it's actually not. It's not clear, just from saying that it's a fluid model and making constraints hold an expectation. I mean, as far as I can tell, it's not actually clear, a priori clear, that the QI should actually be equal to the same Q. So we show that that's good enough in sort of an asymptotic regime. But it's not a priori clear. And I mean, I guess potentially it could even happen. I doubt that it will happen, but potentially it can improve in some kind of, higher order term if you use the time-dependent Q. But yeah, I mean, really the conclusion is that you can use a single Q too.
Yeah. Okay.
Yeah.
Thank you.
Anybody else?
Yeah, I've got a quick question regarding the effort. So in the single customer model, you mentioned that the agent is either fully learns the value or not to learn the value. But in the like multiple customers, you're saying that the agent can adopt a random strategy. I mean, is there any connection or difference between that? And besides this, have you considered the agent can like partially learn the value?
Yeah. So I mean, for the first question, so there's two different things in here. So on the learning side, the agent can flip a coin on any customer and decide whether they learn or not. So that's the Q. And then you're also mentioning the price that you use upon learning. That is actually a deterministic function. So basically, it turns out that the optimal theta I VI is basically equal to VI if VI exceeds some threshold, basically the inventory Lagrangian dual, and it's equal to infinity. So basically no sale if VI is below that threshold, but that is a deterministic function. And then for the other question, so yeah, so basically that would be an interesting follow-up work. So it seems very, I mean, it would certainly be very natural to think about some kind of continuous effort that leads to partial learning. So, you don't either learn nothing or learn the valuation perfectly. Maybe you reduce the variance or like somehow, you have some model of partial learning. You get some imperfect signal at the valuation. And I mean, okay, basically the answer to that is it would be an interesting problem, but one that we haven't gone to yet. But basically, we were stuck on this for plenty of time. That by the time we got unstuck, we just wanted to write a paper. But that would be a very natural
Yeah,
next
I
step.
see. Thank you.
So if there are any questions, then otherwise I'll ask a question. I have a couple of questions actually. One of them is so you define this first best with, let's go to the 1 unit case, right? You have this first best, which is you have like you can observe the values, and there's no like constraints on the the limited liability constraint, right? And this kind of the second best that you look at has the incentive compatibility constraint as well as the limited liability. So I can think of like a first and a half best where I don't have IC constraints, but I do have limited liability constraints, right? So is that, I mean, that problem also seems meaningful in the sense like, okay, what can the firm do if they can observe the values, but they always have to pay something non-negative to the
If they observe the effort.
They observe the effort and so on. Right?
No, in that case, it's tight. So if you observe the effort, you can do it with a contract. I mean, okay.
Yeah. So maybe my question is, I mean, you eventually show that your second best can achieve the first best, so it can clearly achieve the first and a half best, right? Because but I'm
no, like, but even so, I mean, we don't achieve it perfectly. There's an approximation error there. But if you're going to remove, so okay, in this first best problem, so any contract that an expected value is equal to psi works. So I could set the contract to be constant value at psi, and that would satisfy the limited liability constraint.
Okay. Okay. So so limited liability holds for this problem as well, right? So
yeah. So in the first best is I could add the limited liability constraint to this, and I would get the same thing. Yeah.
Yeah. And my okay, so that explains things more clearly for me. And the second question I have is, so you have this assumption that so if I put in an effort as a salesperson, I can learn the customer's values, right? Presumably, I mean, I'm not saying you incorporate this in your model, but I can think of a case where like, if I then charge a price of like exactly equal to the value, then the customer may be like hesitant to like talk to me or like tell me the truth or whatever, right? So that might say that there are some restrictions in setting theta v equal to v, right? So so if you you could either model that explicitly. So that's one approach that one could take and try to like model customer utility and so on. But even in a more sort of simpler case, like if you put some constraints on theta v being less than v, maybe like some factor of v, right? Some factor less than v. So does all your results sort of similarly go through with some minor modifications or like?
I mean, I've never thought about this. I would imagine yes. Like if I constrained theta v to be like some discount times v, I would imagine that I can still tell you what the optimal contract is. I don't know if you'll have to like tilt the contract that I showed you somehow, and I'm not really sure exactly how the the discount would fall in. But yeah, probably you can still say what happens. Yeah. Yeah, and then I don't know if one was to actually properly model the customer as a third layer of agent with incentives. I don't know, probably tricky. Like I know that in online advertising, people think about
Yeah, yeah. It
you know,
seems like
advertisers,
more like
you know, kind of learning the valuation, and then people try to bid untruthfully because of that, and that's already kind of complicated to analyze. So
yeah, maybe having an explicit model is not the way, but like I
Mhm.
mean, intuitively, like if you're talking to me and I reveal my value and then you charge my value, then probably I would be hesitant to, right? So is there if that aspect of the kind of thing can be incorporated, that would be. Thank you.
Yeah, I'm pretty sure that the method should work. Yeah.
Bill, you have a question or comment? Anybody else?